Hydrogen packs massive energy into a small mass, but when put to work, that energy can be extracted in two completely different physical environments. Heavy transport is under immense pressure to decarbonize. Because massive battery packs cut deep into commercial payloads and take hours to recharge, hydrogen has emerged as the necessary alternative. The first path to using it relies on familiar architecture. You can take that hydrogen and burn it in a modified internal combustion engine, an H2ICE. The second path skips combustion entirely. You feed the hydrogen into a proton exchange membrane, or PEM, fuel cell stack, where an electrochemical reaction produces electricity to drive a motor. Fleet planners and systems engineers are now staring down at difficult choice. They have two distinct machines that run on the exact same fuel, but they are governed by completely different physics and engineering constraints. There is no universal winner here. Any claim that one powertrain renders the other obsolete misreads the physical reality of how heavy machinery actually works. Making the right choice requires looking closely at the thermodynamic limits of each system and matching those realities directly to the specific job the vehicle has to do. At its core, the hydrogen internal combustion engine operates as a traditional heat engine. It produces mechanical work by containing high-pressure explosions inside heavy cylinders. This graph plots brake thermal efficiency. As a heat engine, the H2ICE is bound by thermodynamic laws capping how much fuel energy becomes forward motion. Even highly optimized, it plateaus between 35 and 45% efficiency, on par with modern diesel. The PEM fuel cell takes a completely different route. It passes hydrogen and oxygen through an electrochemical stack to generate direct electrical current. Because this process sidesteps the combustion cycle entirely, the fuel cell is not held back by those same thermodynamic limits. Real-world data places modern PEM fuel cell efficiency between 50 and 60%. The physical ceiling is demonstrably higher. That percentage gap is critical at the pump. Hydrogen is expensive to produce, compress, and deliver. For a fleet operator, the rate at which a truck consumes that fuel often dictates whether a route is actually profitable. The fuel cell's electrochemical advantage means it spends meaningfully less fuel per kilometer, driving down lifetime operating costs. When we look at emissions, both systems share one major benefit. There is no carbon dioxide emitted from the hydrogen fuel itself, but the byproducts differ. A PEM fuel cell outputs nothing but pure water and heat. At the tailpipe, it is entirely zero emission. The H2ICE, however, burns hydrogen in ambient air. And that combustion reaches extremely high adiabatic flame temperatures. This scatter plot charts combustion temperature against nitrogen oxides, or NOx. Approaching ideal temperature causes a severe spike in this heavily regulated pollutant. Engineers mitigate this by running exceedingly lean. Pushing the air-to-fuel ratio high forces temperatures down, dropping NOx dramatically. But running lean trades away power density. Even with tight control over the mixture, heavy-duty hydrogen engines generally still require complex physical aftertreatment systems to stay under strict regulatory limits. A hydrogen engine removes carbon from the equation, but it still requires active pollution management. The fuel cell avoids that engineering burden altogether. Where the hydrogen engine reclaims its ground is at the factory level and the repair shop. An H2ICE relies on heavy cast metal parts, reusing a century of proven internal combustion architecture. Manufacturers can adapt existing production lines, and mechanics can use the tools and knowledge they already have. A PEM fuel cell is a far more complex system to manufacture. The intricate layered plates and the heavy use of expensive platinum group metal catalysts drive upfront capital costs noticeably higher. That massive cast metal construction gives the ICE a wide durability advantage in the field. It is built to tolerate heavy vibration, airborne dust, and sustained high load demands. Fuel cell membrane electrode assemblies are highly sensitive to physical contamination, and harsh mechanical load cycling can stress the components, making long service life under rough conditions an ongoing engineering hurdle. Finally, regardless of which converter sits under the hood, both share the exact same physical bottleneck upstream. Hydrogen is a bulky gas. Storing enough of it to move a heavy truck requires thick, high-pressure composite tanks. Those massive tanks eat up significant volume and add weight to the chassis, costing the operator space and payload capacity either way. While the fuel cell delivers superior efficiency, the H2ICE is currently the most financially accessible and physically robust option for demanding, dirty work environments. This branching decision tree helps map the choice based directly on a fleet's primary operational constraints. If the application demands rugged operation in harsh conditions, sustained high power output, and a need to strictly limit upfront capital costs, the data points squarely to the H2 ICE. If the priority is maximizing long-term fuel efficiency to lower lifetime costs, and the vehicle operates in strict zero local emission zones, the PEM fuel cell is the clear choice. In practice, the hydrogen engine serves as an immediate heavy-duty bridge technology built for off-road mining and sectors that punish delicate machinery. The PEN fuel cell acts as the long-term, high-efficiency endpoint for predictable, high-volume freight routes, gaining ground as stack durability slowly matures. But there is one external reality that governs both paths. Neither the engine nor the fuel cell solves the problem unless the industry can deliver clean, affordable hydrogen to the pump at a massive scale. The physical powertrains are engineered and ready to deploy today. The ultimate bottleneck to decarbonizing heavy transport now rests entirely with the energy infrastructure sector.